Okay, hello everyone. Welcome to the second part of single cycle data path. Okay, so remember that our data path only supports add and sub instructions, but we were supposed to handle all the R type instructions, but for now, we must accept that we can only um, handle add and sub instructions. So why is that? Well, the reason, as we've seen from last lesson, is actually because our ALOP is only 1 bit. So we can only tell the ALU to do either add or sub, and those are all the R type instructions that we can do at the moment. So that's the reason why. Now we also have the instruction feeding into the control unit, which wasn't present in the last schematic that we saw this in. But anyway, let's continue. So an important part of what we want to see for this data path is how good is it? So, how good a processor is, as you might expect, is measured by how fast it can execute a specific number of instructions. Say, for example, you had a program that can be supported by this processor would be add sub, and it's a program with a total of 4 instructions, and it's not a very useful program, but it's the program that we can run. So a measure of how fast this processor could is relative to other processors is how fast it could execute these instructions. So in order to measure this, actually, for a single cycle data path, we're going to have to measure the critical path of the data path. So what we have is that the PC changes every clock cycle. Now, we don't want to change the PC before we finish the instruction because that will change the read address and thus the instruction. So we don't want to do that. So, but we want the clock period to be as little as possible in order for our clock frequency to be as high as possible, and thus for us to execute more instructions in a specific period of time. So how do we do that? Well, following what we have below, if we have 10 nanoseconds of delay, 5 nanoseconds for the memory, 3 nanoseconds for the register file, 2 nanoseconds for the control unit, and all registers have 1 nanosecond of delay, what is the highest allowable clock frequency for our data path? Now, the clock period, I would say, has a formula for this, which is the um, clock to queue of PC plus the critical path plus the setup time of wherever we want to write the data into. But since we're not given setup time, we're not going to account for that as of yet. So we only have to account for the critical path and the clock to queue delay. So for this one, we're going to have that we go through, say, the instruction memory. So that's 5 nanoseconds of delay, 5, and then we go through the register file, which has 3 nanoseconds of delay, and then that goes into the ALU, which has 10 nanoseconds of delay. It's, then we go back to the register file, for which we probably have setup time, but we didn't specify, so we're going to have to ignore that one. So I would say this is the critical path of the system. In order to prove that this is the critical path, just analyze the other paths. This other has 10 nanoseconds of delay. That's just 10. This is 5 plus 3 plus 10, which is greater than that. And then we have the control unit, which is 2 nanoseconds. So so that's 5 plus 2 plus 10. RF is 3, so it's actually faster than that. Well, you might say the control unit can go to the into the register file through the write enable, but note that we only need this after the ALU because that's only needed for when we are writing data into the register file. That doesn't actually go straight here, so that doesn't go into 2 plus 3 plus 10. So what we have is actually 5 plus 3 plus 10 going into here, which needs to be longer than 5 plus 2 going into the right enable. So that's not actually something, that's not actually the critical path. So our critical path here is then 5 plus 3 plus 10, which is well, not the data, not the destination. We go through the operands, we get the operands, get another 10 nanoseconds of delay, which is written back into the data. And we need to wait for that entire time before we attempt to increment PC so that we retain the same instruction. So now, the clock to Q is 1 nanosecond plus 5 plus 3 plus 10, which is 18, is 19 nanosecond. So the highest allowable clock frequency would be 1 over 10 to the 19, which is around like 80 megahertz. 19 times 10 to the minus 9. Is this 80 megahertz? 1 over 20 would be 0 0.5. Wait, no, that's not 0 0.5. 0.05 would be 1 over 20. Nano becomes giga. Actually, 50 megahertz. My bad. So that is the highest allowable clock frequency for this data path, assuming these delays. So now we have a performance for the data path. If you see, say for example, some other single cycle data path like the one that we're going to create, again, then you will have to refine the combinational delay or the critical combinational delay, critical path through the single cycle data path, and from there you can measure how long it takes for that data path to execute a specific instruction. So since we can only support add and sub, that is actually a very limited set of instructions. As you may tell, there's only two instructions, add and sub. So we're going to want to add in the data transfer instructions, the load word and store word. So how do we do this? Let's put here the instruction decoding of the data transfer instructions, so we have something to reference while we're writing while we're designing the data path. For load word, these are the stuff that we need to do. So fetch and decode are as usual. We need to do that for all instructions. But following that, we need to do some special things. We need to fetch the base address from the RF. So if you remember correctly, for load and store instructions, we have we write the contents of some register, uh, or we take the contents of some address in memory, that is the base plus offset, and then we write that into the destination register. Or alternatively, during store word, we write the destination register into some sort of spot in the memory, which is which is determined by base plus offset. So in either case, we need to fetch the base address. We need to know what the base is, and we need to know what the offset is. And the offset is determined by this guy, the address, and the base is actually determined by this guy, the RS. So steps 3 and 4, we need to fetch the base address. This is a fetching the operand from RS. And then adding the offset to the base address, we need somehow we need to find a way to put this hard-coded address inside the instruction into the ALU so that we could add it to RS, which is going to be in read data 1. And then after that, we fetch the word to be loaded. So we put that base plus offset into the data memory, for which we can read some data, and then we put that into write data for the register file. That finishes load word. Now for store word, it's the opposite, or rather, it's the same all the way up to 4. We still need to fetch the base address, and we need to add an offset to it. But in this case, we need to fetch the word to be stored from the register file. So Actually, RT, in data transfer instructions, it's not RD. We don't use RD. We use RT for the destination or the data source. So we read RT from the register file, and then we write that into the memory pointed to by the address that we've calculated from RS plus offset. So let's see how we're going to be able to do that. So RS goes into the read data 1, which is the base, which becomes the base address. So that's what we saw earlier. RT goes into read register 2 and becomes the store operand if it's a store operation. And for an instruction, for a memory instruction, we need to put RT as the right register in case it's a load word instruction, because RT is now the destination if it's a load word. We need to put that into the right register. And in order for us to use the address inside the ALU, um, we take that from the instruction as well, and we put it into a sign extension block to get the offset. So what does the sign extension block do? Well, if we go back a slide, you can see here that the address is actually only 16 bits. Now, what's the problem with being 16 bits? Well, the ALU works with, say, this guy. This is 32 bits. So, adding a 16-bit offset with a 32-bit number is not actually very well defined, or rather, it's not something our ALU is equipped to actually do. So, what we can just do is say we have 16 bits, that's 4 hex values. We have a a a all right, okay, so that's 1010 for this one, for the say leftmost a, that becomes 1010. Now sign extension makes it so that the rest of the 32 bits becomes 1 in this case. Why does it become 1? Because this is the sign bit for the 16 bits that we have initially. So sign extension means you repeat the sign bit all the way. So that if you do that, it keeps the sign. If, for example, we added zeros to this one, the number changes sign, and so the number changes. So let's say it was not 8. 8 is okay. It was 7 a instead. So in this case, 7 would become 0111. And so, to sign extend that, we just copy the last bit all the way 0. So it becomes a 32-bit 7AAA. OX 7AAA represented in 32 bits. And this one becomes um, uh, OX AAA represented in 32 bits while preserving the sign. So that's why we need to sign extend or just regular extend. So from that, we get the required address offset. So furthermore, we had RS being fed into here and RT being fed into here. So now we have the base address that we read from RT. We feed that into the ALU. And then now we have the address offset that we calculated from the 16-bit address. And we feed that into the ALU as well. So since we want base plus offset, we tell the ALU to do the plus operation. And then we feed the result into the address of a data memory. So remember, this is not the same memory that we used for the instruction. So remember, we had like something like the instruction memory over here on the other side. So in this, unlike the most popular regular computers that we have now, the instructions and data are stored in separate memories in this processor that we've designed. And this is actually called the Harvard architecture. This in contrast with the Princeton architecture, where the instruction and data memory are actually the one and the same. But anyway, we have the write enable for the data memory, of course. So you don't want to write anything into it if it's a load instruction. And then from the address, we get the read data. So this is the value pointed to by base plus offset. And then we put that back into the right data if it's load word. So now here, um, the other thing that happened is actually we were putting RT actually into right register. So um, then the value pointed to by base plus offset will be put into right data, and the right register is RT. So say for example, it was a load word that we were doing. We put right enable as 1, and so we will write the data pointed to by base plus offset into the register RT. But what if we were doing a read for a store word instruction? So here um, we preserve everything. But the thing that we're is relevant to us now is that the RT is also pointing to is also put into read register 2, and thus read data 2 actually what comes out of read data 2 is the value pointed to by RT, which puts it into the right data port of the data memory. Now since it's in the right data port and we have base plus offset pointing into the address, we just have to put memWrite enable as 1 and write enable as 0 if it's store word. So um, for load word, we put 1 as the write enable, but nothing else changes. For store word, we put 1 as the memWrite enable, but nothing else changes. Of course, the other write enable will be 0. So if this is 1, this is 0. If this is 1, this is 0. Okay. And with that, we're going to have we're going to have support for the load word instruction, for the load instructions, or for the memory instructions. And we have a few let's say problems from what we've done. For the rect register input of this guy, for the R-type instructions, we needed RD to be put in it. But for the load and store instructions, we had RT to be put in it. So in order to solve that, we're going to put a multiplexer that has to choose whether to put RT or RD into right register. So if it's a load instruction, for example, so we had a load word instruction, the destination selection would be 0 because we want to choose RT. But if it was, say, an add or sub instruction, we would choose RD, which would be 1. So I assume the way we choose registers is actually if 0, the top one, if 1, the bottom one. So that's the way we solve that one. Of course, for ALU as for the ALU input as well, we either have to choose from read data 2 or the offset. So we needed a MUX for this part as well. Lastly, we needed to add a MUX for the output so that we could choose what to put into the right data of the register file. So if I was an R-type instruction, I would want to choose the output of the ALU result. But if I was a load word instruction, then I would choose the output of the data memory. So that's why we have a MUX there. And that completes the single cycle data path with support for add sub, load word, and store word. So summarized here is the needed control signals. I've already mentioned earlier. So you can just go back to the to that part. So here, at least the part about multiplexers I've already mentioned. For write enable, if it's a store word, if it's wait, write enable. Okay. Rather this is load word. Okay. Yep. So here, write enable, that is for the register file. If if it's an R-type instruction, which is add sub, and we want to write something into the destination register, then it's asserted. If it's a load word instruction, we also assert it, but otherwise we deassert it. But the only otherwise case here would be store word. Now, if it's a store word instruction, we assert memWrite, which allows us to write into the data memory, but otherwise it's deasserted. Alloop depends on the func field, as before, either add or sub, or and then or, but we didn't have, it depends on the design of the allo. If I type, it's set to addition. Why is it set to addition? Because we want to calculate base plus offset. Note here, we plus. It's base plus offset. So, okay. Moving on. Next, we want to support branch instructions. Now, if we can support branch instructions, then that would actually complete the processor for a lot of useful programs. So let's try to support branch instructions. So what do we need to do for this? Remember that branch instructions change what's inside the program counter. Why would they need to do that? Well, what's inside program counter determines which instruction we're reading, and with branch we want to change the next instruction. So what would be the next instruction is what's going to be the next program counter. So we interfere with PC+4. We don't write PC+4, but we write some other address into PC, and that's how we do branches. So first we fetch and decode the instruction. Those are the two for the as always the first two steps. And then we add an offset to the base address. So what do we mean by this? Branch instructions have an address offset. As actually, it's an offset in number of instructions. So say, because it's address offset over 4, this is number of words. So this is like say for -3, this would be 3 instructions up, like 3 instructions before, or if it was like say +2, this is 2 instructions after the branch. So we want to add the offset to the base address. So what we do is we calculate PC+4 plus the address offset. Remember, why is it address offset instead of word offset? Well, PC+4 is actually in bytes. That's why it's 4, right? So it's not PC+1. It's PC+4. So then address offset is the instruction offset times 4. So that's why it's address offset. So it's PC+4 plus address offset that we need to calculate in order to write it back into the PC. And then we also need to fetch the operands to be compared. So that is RS and RT. So say our if is depending on RS and RT. So it can either be equal or not equal. Then branch is what we're trying to do here. And the way we do that, I've already mentioned this earlier, we subtract one operand from the other. So that is RS minus RT. Now, what happens here is if RS equals RT, then the zero flag would be 1 because RT equals 0 there. But if RS was not equal to RT, then the 0 flag would be 0. Why is that? Because RS is not equal to RT, so RS minus RT would be some integer, say C in G. So the 0 flag would be 0, and this 0 flag is what we use to determine whether or not we're actually going to write a thing into the PC. So step 6, replace the PC with the target address, the calculated target address. You see here, this is the branch target address. you replace the PC with the branch target address if the branch is true. So what happens then is that the next instruction that will come out of PC will be the branch target instruction. So let's see how we implement this. So we have here, we go from PC. We had PC right here, and then it gets added to plus to 4, so that's PC plus 4. And then we have the address offset feeding into this adder over here, and then we get VTA here. So the branch target address comes out of this instruction. So from the branch instruction, we once again fetch some sort of address, and then we sign extend it so that it's 32 bits, or rather, actually, well, it doesn't matter if it's 32 bits. But what we do with it, okay, let's say this is 32 bits. This still would have to be 32 bits because that's a 32-bit adder up there. So why do we do shift left of 2 over here? Well, what we do with this is actually we're basically multiplying by 4. Because you see, shifting left means that you're multiplying 2. So what do you mean by this? Say this is 0101, which is 5. If you shift left, this is actually 10, or A. And another example, this is 10, which is 2. This becomes 100, which is 4. So if you shift left by 1, then you multiply by 2. And so if you shift left by 2, then you multiply by 4. And why do we need to multiply by 4? Well, remember that this address that comes from the branch is actually in number of words. It's in number of words or number of instructions. So we need to multiply that by 4 to get the actual byte addressable memory address offset. So since we multiplied it by 4, then we get the actual address offset that we can put into PC. And so we get the target address from that. And what do we do from the with the target address? Well, it depends on the RS and RT that we have. So let's see how we connect that. So here, what is new here? Well, we still have the shift left, and we have the sign extend that we have the shift left. We use the same sign extend on both the word address and the on the load word and store word address and the branch address. But the difference with branch is we shift left by 2. The extra thing here is that we calculate a cell PC from this. So what cell PC chooses between well, the two things that cell PC chooses would either be PC plus 4. So do we put in the next PC, or the output of adder, which is PC plus 4 plus offset, or more clearly, we call this the branch target address, so where we want to go. And the way we determine cell PC is, in this case, comes from 0. So this goes actually into the control, and then the control looks at the 0 control signal of the ALU and determines what goes into cell PC depending on whether or not it's branch if not equal, or branch if equal. So say for example we had a B and E instruction. So if RS and RT are not equal, then we should branch. So here we have RS going into RT. So we go through here, of course, and then we put that into the ALU. ALU op would be a minus, and then the ALU result. We don't need the ALU result in this case. We just want the 0. So if RS and RT, the 0 bit will be this. So if it's branch if not equal, cell PC would be, if RS equals RT, then RS minus RT would be 0. So then we don't branch if 0 is uh if 0 is 1. So if cell PC is 1, then we choose this. That meaning we branch. Or if cell PC is 0, we don't branch. So that means that for branch if not equal, if RS minus RT, if is not equal to 0, then that means if 0 is 0, then if 0 is 0, then we branch. So that is not Z. And then if it's branch if equal, then RS minus RT has to be 0 for us to branch, and that means that we put Z into cell PC. Okay. So okay, these are the control signals. So well, as summarized here, this is the old stuff. Well, these three are the are the old stuff. And then cell PC is the new stuff here. We've already discussed what cell PC is. It's if branch if not equal, it's not Z. If branch if equal, it's Z. Here we have, well, write enable, memwrite, and alloop. So if it's branch, then it's alloop becomes subtraction. So that's the only thing that we added in the other signals of control signals. And that's basically it for the single cycle data path. So we can now support load word. So as a review, we support add, sub, load word, store word, branch if equal, and branch if not equal with these with this data path. And you could actually do a bunch, quite a bunch of things with these. Like for example, building a Fibonacci sequence generator. You can do that with this without hard coding. Like just pure bunch of add subs. You need to use for loop for that, and your for loop can be done with branch if equal and branch if not equal. So just to review, we wanted to build a reprogrammable computer whose state machine depends on the input instruction. And with this, we've actually achieved that. So from state 1, we read an instruction and then we write something into either the register file or the data memory, which leads us into another state, which is state 2. And then we read another instruction, which leads us to change the data memory or the instruction memory, the data memory or the register file, which puts us into another state. If we read an instruction that we don't know, that is a NOP, then we go back to the same state because we don't want to write anything. Also, if branch is not taken, then we go back to the same state. Actually, never mind. We don't go back to the same state. We actually go to another state because PC is part of the state. So even just PC plus 4 is going to another state. And because there's so many registers and there's so many other things in the there's so many state variables in the data path, then there's going to be a countless number of states for our reprogrammable computer. But with this with this computer, we've already been able to implement most instructions that we find useful. So thank you, everyone. I'll see you in the next module to discuss the multi-cycle data path. So for this module, we won't be having a quiz, but we will be having a problem set that will be released along with the second week of the multi-cycle data path. So please look forward to that.